Everyone, welcome to Yebo Physics on a Tuesday afternoon. I hope I find you well. My name is Arnold, and I'll be joining you this afternoon as we solve some physics problems together. We're going to be looking at questions on mostly on fluid mechanics and a few questions on wave motion. First and foremost, I just want to check if I am audible. I can see I've got some company on Teams. Lilita, could you please confirm if you can see the screen that I'm sharing?
Yes, I can see it.
All right, thanks for confirming. So I'm already showing the first question, and this question is on Newton's law of gravitation. So I'm already sharing the first question, and we're going to be looking at more questions on mostly on fluid mechanics. So the question reads, three uniform spheres of masses m1, m2, and m3 are placed at corners of a right angle triangle as shown in the figure. Calculate the resultant gravitational force on the object of mass m2, assuming the spheres are isolated from the rest of the universe. So assuming the spheres are isolated from the rest of the universe. So what are we supposed to do there? We're supposed to apply Newton's law of gravitation. What's the equation? We know that F is equals to G m1 m2 over the square of the distance of separation. So now we can see that we have got three bodies acting. So we want the net force, right? The net force. Yes, we want the net force. Calculate the resultant force. So I'll just say F net. So first and foremost, if you look at, you've got M3 on M2, and you've got M1 on M2, right? So which means that you have your forces like F3, but you can plus F3 on 2 and F1 on 2, because 2 is our reference. Okay, this is our point of mass in question. So we can start with the x-axis, where we've got our F, where we're looking for F3 on 2. So we're going to be substituting into this equation, which we have already written down. We'll be substituting into that equation, and the value of G is known as 6.67 times 10 to the negative 11 multiplied by the value of M3. What's the value for M3? 6 kilograms times 6 kilograms multiplied by M2, which is 4 kilograms. And what is the distance of separation there? From there to this point, the distance of separation, we can see that it is -4. So which means that's 4 meters all squared, because we have to square the distance of separation. Once you've done this, then you can obviously punch this. You can also punch along and confirm if we get the same answer. And if at any point you need any clarity, please let me know. over 4 squared. Right, so that'll be 1.0 multiplied by 10 to the negative 10 newtons. And if you had to add direction, you would see that this sphere M2, because there's a force of attraction, it will tend to move to the left. Right, so this will be in the I direction. And if you were to put the if you had to put the vector to be in the I direction and it's negative, then you do the same thing for F1 on 2. F1 on 2, 6.67 times 10 to the negative 11 multiplied by M1, which is 2 kilograms. 2 kilograms multiplied by 4 over the distance of separation. So you can check the distance of separation there, it's 3. The coordinate there of M1 is 0, 3, 0, 3. So that's 3 meters separating. So that's 3 squared. Now you can punch this. So instead of 6 there, now we have got 2. We've got 2. And instead of 4 there, we have got 3. Okay. Therefore, we get our answer is 5.92 or 5.93 rather, times 10 to the power of negative 11 newtons, and this is in the positive J direction. So you can give your answers in this form where you're simply adding the two vectors with their vector direction, or you can choose to find the magnitude. Right? If you are to find the magnitude, you can then calculate your F net being equals to the square root of F in the I direction all squared plus your F in the Y direction all squared. Therefore, you get your resultant. Okay, but I'm not going to show this. I'm not going to compute, but I've actually shown you how to calculate the independent forces. And then to find the resultant, it will be the combination of two vectors which are perpendicular to each other. And you already now know how to deal with two vectors which are acting perpendicular to each other. So you can work that to the end if you like, or you can present your answer in this form. All right, that's question 1. I just forgotten. Perhaps I can record. Let me record the meeting in case. Right, did you manage to follow this working?
Yes, I did manage.
All right, sure. So that's more like warm up, getting the ground warm and running. Now let's look at question 2. So the rest of the questions, or most of the questions, are on fluid dynamics, you notice. So question 2. It reads, a swimming pool has dimensions of 30 by 10 and a flat bottom. When the pool is filled to a depth of 2 meters with fresh water, what is the force exerted on the bottom Let's put one on the bottom, on each end, and on each side. Okay. So here the principle is on computing pressure. You know that pressure is equals to the force over the area. Okay. It's equals to the force over the area. But how can we find the force? How can we find the force? In this case, that force will be as a result of the weight of the water, right? It will be mg over the area of interest. Okay, but you remember that density is equals to your mass over the volume. So your mass is equals to your density times your volume. So which means that in place of mass there, it will be your density of water times the volume over the area of interest. So this is how you would calculate your pressure. Now, we can work out, you can see that the question is asking for pressure on different uh, sides of walls of the pool. So the first one that is being asked is the flat bottom, which would be the length and the width, the product of the length and the width. So if this is your swimming pool, this is your width, this is the bottom of the pool, and this is your length. And obviously we cannot see the height because this is showing 2 dimensions. So for part 1, we can substitute our pressure equals to density of water must be 1000 kg per cubic meter. Then the volume of the water will be your length by width by height, which would be 30 by 10 by 2 multiplied by 9.8. Then your area of interest, now it's only your length and your width. Your width should be 10 multiplied by your length, which is 30. Let me know if you agree with what I'm doing. All right, so there we are. The answer that we're getting, there we are. What do we have there? We're getting 19,600. What do you say about that answer? Did we perhaps miss something there? Because we want to find the bottom side. The bottom side would be ideally your length and the width and acting downwards. So that is the first part, which is similar to the second part again, that you're being asked to say find your area or your pressure on each side. Now, if you're now looking at the sides of the pool, you're basically your area, the sides of the pool now would be, the sides of the pool now would be, each side will, to find your area, you'll now have your depth, which is 2 meters, multiplied by the side of one length. Okay, so you would still use the same equation, which will be your pressure equals to your density of water times the volume times the value of G over the area. So this is the same equation that you would use for that problem. The only change that you'd make when you're now looking for the last part would be to find the, it will be to determine, it will be to determine the area of interest. But otherwise, the density of water is known. The volume of the water is constant, which will be your length by width by height, 30 by 10 by 2. Then after determining that, multiplied by G, that's your mass, mass by G to get the weight of the water. So the weight of the water will remain constant. It will not change. Okay, the weight of the water will remain constant. It will not change. And then after that, you divide by the area in question. For example, the first part was the bottom side. Then the second part was, the second part will be the on each end and then on each side, on each side. So I hope that you would be able to compute the remaining parts. I would not need to work them out. Now let's look at question 3. Question 3, you can read it up. What does it say? A table tennis ball has a diameter of 3.8 centimeters and average density of 0.084 grams. What force is required to hold it completely submerged underwater? Right, so you can identify the forces that will be present. Force is present. First, you're going to have a force that is being applied. Force applied. Also, you've got the weight of the ball. Then, obviously, you have your buoyancy. All right. Your buoyancy. So the applied force would be going down, right? Because you want to apply it so that you submerge, to be going down. Your weight, obviously, it's going down. Then your buoyancy would be acting upwards, right? So, which means that if you are to sum this up, your buoyancy minus your force applied minus your weight should give you a resultant of 0, such that your buoyancy is equals to the applied force plus the weight of the ball. But what do we need? We need to determine the applied force. So the force applied should be equal to the buoyancy minus the weight. Now, what is our buoyancy? You must now know that your buoyancy is equals to the volume of the displaced fluid times the density of the fluid times G. By now you should be knowing this equation. So what does this give us? So it means you can now substitute for a buoyancy, density of water times G minus mg, right? You can then further simplify, because the mass of the ball we are not given. We can now express it in terms of density and volume, because the mass of the ball we are not given. So it will be product of the volume of the ball times the density of the ball times G. Now you can factor out the volume displaced by the water is equals to the volume of the ball, and G is common, so you have your density of water minus your density of the ball. Now you can substitute what are we given there? Diameter, average diameter with an average density of that. Okay. Right, so now as you can see, you have got the density of the water. No, the density of the water, it's known, rather, you're not given. The density of the water you're not given, but it's 1000 kg per cubic meter, right? That's the density of water. And you are given the density of the ball in gram per cubic centimeter, so which means you would have to convert that. But the volume of the ball were not given, but you know that volume is 4 of a sphere, 4 over 3 pi r cubed multiplied by your G minus your density of the water. Density of the water minus your density of the ball. So what you then have to do is to convert the density of the ball into kg per cubic meter. You've done conversions, right? Then afterwards, then you can be able to punch and determine what your force would be, right? And see if you get that value that is shown there. So I will not substitute further. You will do the substitution and see if you get that value. But remember, as you do the substitution, make sure that the diameter is converted into a radius, which is in meters, and also make sure that your density of the ball has been converted to kg per cubic meter, right? So you make sure you do that. You should be then able to obtain your answer as shown there. So I'll not break it out further. You will do it just to check and see if you get that value. If there are no questions, we'll move on to question 4. Question 4 says, a cube of wood having an edge dimension of 20 centimeters and a density of 650 kg per cubic meter floats on water. What is the distance from the horizontal top surface of the cube to the water level? What mass of lead should be placed on the cube so that the top of the cube will just be level with the water? So this question is in 2 parts. First, we want to calculate what is the distance from the horizontal top surface of the cube to the water level. So this is the scenario that we have. We have got our cube there, which is partially immersed in water. And now this is okay. Okay, all right. Question says it's a cube, right? So I should make it look like a cube. Right, so it's partially immersed and you've got a distance h protruding there, and the sides are 20 centimeters, so which is 0.2 meters, and here's 0.2 meters as well. So this height unknown there becomes h becomes equals to, okay, that unknown distance, all right, it's fine, we'll leave it as h, and here would have L minus h. Okay, the total length minus h would give us the remainder. Now let's understand the question, right? Let's understand the question. We're supposed to find the distance from the horizontal top surface of the cube to the water level. So that value h. So first and foremost, we can determine this from knowing about our buoyancy, right? Because that is what is keeping that afloat, all right? And it will be equal to the weight of the block, right? So first and foremost, remember that your buoyancy is equals to rho Vg, okay? And this is equal to your density, then multiplied by your volume of the displaced fluid, which would be the length times L minus h. That is the volume of water displaced, right? And obviously multiplied by your G. And this density is the density of of water, right? If you have to simplify this, then your density of water will be equals to L squared L minus H times the value of G, that's your buoyancy, okay? And this should be equal to the weight of the block. So we can then equate the value, because we know that the buoyancy would be equal to the weight, right? Buoyancy being your upward force and weight being your downward force. So also remember that your weight will be equals to mg, and your mass, it's the density times the volume times g, right? But in this case now, it is the density of the wood. That's why I've denoted by WD, all right? So you can simplify this, should be equal to the density of the wood, then the volume of the wood, it's L cubed, length times width times height times G, all right? Now equating your buoyancy to equating your buoyancy to weight, you would now have an expression of density of water, L squared L minus H times G, equals to density of your wood, L cubed times G. Then you can cancel what is common. This goes, this goes, this goes, that goes, okay? You remain with L minus H being equals to the density of wood over the density of water times L, right? So such that if you make H the subject, you will now have take that to the other side, it will now be HL minus density of the wood, density of water, like that. Then for simplicity, H would be 1 minus the density of the wood over the density of the water. You factored out L. And the L, you know, it's 20 centimeters, right? And the L is 20 centimeters. The density of wood you're given, okay, we can work out this one. The length is 20 centimeters, which is 0.2 in meters. Then you've got 1 minus density of the wood, 650 over density of water. Then you can compute this. Okay. Let's see if this is what is expected of us. That's quite different. That's okay. because I missed a zero there. Should density of water should be 1,000. So that gives you 0.07 meters, which is the same as 7 centimeters. So if you want, you can just punch this as 20 centimeters. Gives you straight 7, but remember that would be in centimeters, right? So this is how you'd find your height h, which means that this is 13 centimeters, and that is 7 centimeters. Now the question goes on. The question goes on to say, what mass of lead should be placed on the cube so that the top of the cube will just be level with the water surface? Now you still have your cube. And the question is asking what mass of lead should be placed there such that the cube is just immersed like that. Such that the cube is just immersed like that. So now you can identify the forces that will act on this system. First, your buoyancy will be acting up. You'd have your weight of the block, and you'd have the weight again of this lead, isn't it? So which means now that if you had to form an equation, your buoyancy will be equals to the weight of the block plus the weight of the lead. All right. The weight of the block, remember we did compute earlier on. The weight of the block you did compute earlier on. Where is it? It's this one. This is the weight of the block. So what was the expression? The simplified expression. Weight of the block is just the density times L cubed times G. Right. Then what mass already your buoyancy you did calculate earlier on, so I'll leave that for you to, you can simplify that further and see what you'd get after substituting to determine the mass of the block. Right, so we're simply using this equation to determine what then would be the mass, so that the water surface is just level with the block, right? Just imagine. Now you know how to calculate your buoyancy. We did calculate it earlier on. And now your buoyancy will now be the volume of the water, which is the density of the water. B is equals to the density of the water, volume of the water, times G. And in this case, now the volume of the water displaced would now be L cubed as well times G, isn't it? So we'll now have a scenario. Okay, this is volume of water. So this should be WD. This is WD, weight of the block, WD. Then here, then you've got density of the water, L cubed G equals to the density of the wood, L cubed G plus M, right? And then you then collect like terms, and then find your value for the mass. I'll leave you to work that out. Now let's look at question 6. If there are no any comments or questions. Question 6. Oh, question 5 rather. We're doing question 4. So it's a question on some simple harmonic motion, and x equals to 5 sine pi t plus pi over 3. So, and you're being asked to find, okay, this is the displacement time according to the equation. Bodies oscillating in simple harmonic motion. We know that x is equals to x naught sine omega t plus your phase. Okay. So now we need to determine the velocity, but we're given a displacement time relationship. So we can differentiate that dx over dt. So if you integrate, differentiate that expression, that will be 5 pi, differentiate sine, you get cos, right? Cos pi t plus the phase difference. All right, so this is equals to the velocity. So now you can punch v is equals to 5 pi cos pi plus pi over 3, because we're told that the time is 1 second, or at 1 second, right? Now you can punch this and see. And the most important thing here is to make sure that when you punch, your calculator is in radians. 5 pi cos pi plus pi over 3. We get 15 points. Oh, why do we have none of the above? T is equals to 1 second. Oh, it's in degrees. I just said don't forget to put your calculator in degrees, in radians, and I've just forgotten. So your velocity will be negative 7.9 meter per second. So don't forget to put your calculator in radians when you punch for the velocity. Okay, so that's what you questions 6 up to 10, they've been worked out in the previous tutorial. So I'll quickly go out and get more questions from tutorial 7. There is load shedding starting at 4 p.m. That's like 7 minutes from now. I'm not sure if this will go as per schedule, and if it does, don't be surprised when the stream ends abruptly. Okay, so let's find more questions, and fingers crossed that either the load shedding will be delayed until we finish, or it won't be covering this area at form, maybe later. I can quickly check, the schedule whilst you are reading the first question. Okay, so it seems there won't be load shedding soon, but it will be at 6, so we still have some time to go through the remaining questions. So we should be able to go through this and finish without any disturbance. Now let's look at the question displayed. So that's question 1. So it says a blimp is filled with 200 cubic meters of helium. How much mass can the balloon lift? The density of helium is 1/7 that of air, and the density of air is 1/8 of that of water. Consider the mass of the balloon is negligible. All right, it's a very interesting question. So now again, since it's fluid mechanics, we can identify the forces that we have on that system, right? So obviously we will have a buoyancy force acting upwards. We have our buoyancy acting upwards, and we already know that our buoyancy would be equals to the density times the volume times g, and in this case we're talking of density of air. All right, and what else is there would be the weight of the helium, right? Let's pump with helium. So the weight of helium, obviously weight should be going downwards, right? Which would be equals to the density of helium multiplied by its volume times g. What else could we have? The mass. How much mass can the balloon lift? Yes, so how much mass can be lifted up? So obviously that mass has got a weight. So the weight of the mass, we expect it obviously to be going down, which will be equals to mg. So now if we were to put this in an equation, so this would be B minus weight of helium minus the weight of the mass to be lifted up should be equals to 0. Now we want the weight of the mass will be equals to your buoyancy minus the weight of helium. All right, now we can simplify mg, and our buoyancy, we've said, is the density of the air times the volume times g, and weight of a helium will be density of the helium times the volume times g. The volume will be the same because the volume that the helium displaces should be equals to the volume of the helium itself. Then you can cancel what is common, can cancel what is common, that is common, that is common, that is common. So your mass then becomes that factored out density of A, right, minus the density of helium. So if you are to simplify now, your density of A, what is the relationship between density? The density of helium is 1/7 that of A, okay? So the density of helium is 1/7 that of A. That's what we're told. Density of helium is equals to 1/7 the density of A. So nothing to worry about there. Now we can substitute, right? Or we can simplify this. So if you've got a 7/7 minus 1/7, that should be 6/7, right? You simplify that, 6/7, the density of A, multiply this by your volume. So that will be 6/7 multiplied by the density of A, which is 1/8 that of water. Remember, we've been using the density of water earlier on. The density of water is 1,000, right? So 1/8 of 1,000, 1/800 times 1,000 would be your volume. So this will be 6/7 multiplied by 1,000/800 times the volume of helium, which is 200. I hope I did not lose anyone along the way. So this would be simply, just punch it as it is anyway. So that would be 6/7 multiplied by 1,000/800 multiplied by 200. Get 214, do we? Yes. So we do have an option of 214 kilograms. So that's how you would work out your mass. So the first thing that you did was to identify the forces that are there. First, you've got your buoyancy. It's expected because of the displaced fluid. Then you've got the weight of the helium. Then the weight of the mass that you want to lift. And identifying the directions, then you can form an equation, knowing that the weight of the helium acting downwards, the weight of the mass is going downwards, the buoyancy obviously upwards. Then from there, you're just substituting until you get your ideal mass. So the ideal mass that would be lifted would be 214 kilograms. That's a lot. Then question 2. All right, so this is somewhat some theoretical question. I'll leave this to you to read about this. And in case you may have any questions arising on that one, then you can let me know, we can discuss it. But for now, let's delve into some calculations. So quickly go to question 3. A hydraulic lift raises 2,000 kilogram automobile. When a 500 Newton force is applied to the smaller piston, if the smaller piston has an area of 10 square centimeters, what is the cross-sectional area of the larger piston? Okay, so we can have an illustration to this. So lift a 200 kg automobile. So this would lift a 200, is it 2000? 2000, yes. Kg. So it will be lifted on this other side, going upwards, and here, applying a force of 500 newtons. And what area do we have? Smaller piston has got an area of 10 square centimeters. And in here you've got an incompressible fluid, which is form of a liquid. Right, so the question says, what is the cross-sectional area of the larger piston? Okay, so this question resolves the principle of pressure. So because liquids are incompressible, therefore the pressure transmitted from the smaller piston to the larger piston would be the same. So the pressure at the smaller piston and the pressure at the larger piston would be the same. The difference now is the area. Okay, the difference now is the area. So to know the area at this point, we should know the pressure. Okay, and we can know the pressure by using information given at the smaller piston, because we've got the force and we have got the area. When we get that pressure, we can substitute it here, because we've mentioned that the pressure exerted at this point will be the same pressure exerted at the master cylinder. So now let's find the pressure. So already we know pressure is force over the area. What is our force? It's 500 Newton over the area, which is 10 square centimeters. Take note, I leave it as square centimeters because you can see that the solutions, they require it in square centimeters. So this will be 50 Newton per square centimeter. So that is the pressure that we will substitute at that point. So now our area, to find the area of the master cylinder, will be equals to the force over the pressure, which we've just determined. Then what is our force? It's the weight of the car multiplied by 9.8 over 50. You can leave out the units. I already know that this should be in square centimeters. So punching that, what do we get? 2000 multiplied by 9.8 divided by 50, we get a very large value as expected, 392 square centimeters. So this will be the area of the larger piston. So the main principle that you should keep in mind there is that liquids are incompressible, therefore the pressure exerted on the slave cylinder should be equal to the pressure on the master cylinder. So the pressure on the smaller cylinder is equal to the pressure on the larger cylinder. And then knowing the pressure and knowing the force or the weight of the car to be lifted up, you can then determine what area that car would be sitting on. So this is the principle that is commonly used on some hydraulic jigs. Okay, question 4. I don't see any questions so far. Let me check on the other side. No question as well. So I hope you are managing to follow. Let's proceed to question 4. All people come very close to being able to float in water. You should try this. Yeah, you should try this. When you're in a swimming pool, try to allow yourself to float. You'll be a little bit partially immersed, but what you have to do is to open up your hands, spread a bit your legs. While doing that, you're trying to increase your area, because once you increase your area, you are reducing your pressure. So which means you have got a larger surface area and less pressure going downwards. So all people come very close to being able to float in water. What therefore is the volume in cubic meters of a 50 kilogram woman? Okay, so we've been given some parameters there. So obviously, if they are to float on water, you have two forces that are going to be acting there. You've got your buoyancy, okay, and you've got your weight going downwards. So which means your buoyancy plus the weight should be equals to 0 actually, right? No, not plus, should be negative. Should be negative. So which means your buoyancy should be equals to your weight, or either way. So now you know that your buoyancy, we're talking about the weight of the fluid displaced, right? So the weight of the fluid displaced would be the density of water multiplied by the volume times G and equals to the weight times G equals to mg, right? Now you can look at what is common. That is common. Therefore, your mass, we're looking for the volume. Therefore, the volume would be equal to the mass over the density of water. Okay, and in this case, the mass you're given is 50 kilograms, and the density of water is 1000 kg per cubic meter. So if you compute that, then you get an estimate value of 50 over 50 0.05. So that would be an estimate. So you can, if you know your mass, you can estimate what you, if you know your mass, you can estimate your volume, right? I know my mass, I can estimate I'm somewhere almost in the 80s, there. If my estimation is something to go by, so that will be my volume. So you can estimate yours and see what it would be, knowing your mass, of course. So, okay. Now let's look at question 5. Question 5 reads, an empty spice bottle has an inner volume of 1.3, 1 times 10 to the negative 4 cubic meters. it has a mass of 112 grams when filled with air, and it displaces that amount of volume of water when fully submerged. Okay, what volume of mercury must be added to the empty bottle so that it would just submerge? Okay, now you can identify and form an equation from that scenario that you have. Okay, so in this case, first and foremost, you want to determine what would be the weight of that mercury so that you can find the volume of the mercury. Right, so if you had to have the weight of the bottle plus the weight of your mercury should be equals to the weight of the water. Right. Yeah, that's the volume of the water when okay, that's the weight of the water when fully submerged. Right, so which means that the weight of the bottle plus the weight of the mercury should be equal to the weight of the bottle and the mercury. Okay, so let's look at the parameters that were given. The weight of the bottle, it's 112 grams, which is times 10 to the negative 3. That's the mass multiplied by 9.8. That's, and we are looking for the weight of the mercury equals to the weight of the water, which is the density of the water times the volume of the water times the value of G. Right, so which means the weight of mercury will be equals to the density of the water. We know it's 1000. Volume of the water is given 1.63 times 10 to the negative 4 times 9.8 times 9.8. All this minus 112 times 10 to the negative 3 times 9.8, so that we get the weight of the mercury, and from the that will simplify our problem. (1000) times 1.63 times 10 to the power of negative 4 times 9.8 minus 112 times 10 to the power of negative 3 times 9.8, get a value of 0.4998 newtons, right? But we are not looking for the weight, we are actually looking for the volume, right? But we know that weight of Hg will be equals to the density of the mercury times the volume times G. Now we know this, right? So now we can substitute, or make V the subject first rather. V will be equals to your weight, which we've just obtained, divided by your density and the value of G. And the weight you've just obtained 0.4998 over the density of mercury, which is 13.6 times 9.8. Then you can determine that in form of calculation. That would be 0.4998 over 13.6 multiplied by 9.8. That's the value that you get. Okay, that will be 0.00375 in cubic meters, and to get, which is equivalent to multiply that by 1,000, you should get 3.75 cubic centimeters. So conversions, you'll still be familiar with conversions, but that is how you'd go about that type of a problem. So that was question 4, right? 5 rather. You can look at question 5 to see what type of a calculation do we have. Question 6. A super tanker, a super tanker filled with oil has a total mass of that, if the dimensions of the ship are those of a rectangular box, 300 meters long, 80 meters wide, and 40 meters high, determine how far the bottom of the ship is below the sea level. So given the mass, the dimensions of the ship are those of a rectangular box, 300 meters long, 80 meters wide, and 40 meters high. Okay, so determine how far the bottom of the ship is below the sea level, right? So obviously this is just a question on buoyancy and the weight. So identifying your two forces, you've got your buoyancy going up and your weight going down, which is your Fg, and your buoyancy is the density of water volume times G equals to mg, right? You can cancel what is similar and what is similar on the other side. You can substitute the density of the water, you've got 1000 multiplied by the volume, which you do not know. Then you have your mass 6.1 times 10 to the power of 8. Right. So you can check what would be the volume displaced. The volume displaced would now be 6.1 times 10 to the power of 8 over 1000. Right. So that would obviously should still be 6.1 times 10 to the power of 5. Right? 1, 2, 3, 4, 5, 6.1 So this is your volume, displaced. Oh, the density of sea now, or sea water, okay, it's 1020. So I can't use 1000, the density of water, 1000. Okay, so let's change that. I had missed that I used density of water, which is 1000. So in this case, it's 1020. It's a bit more dense compared to fresh water. So obviously this value changes to 598,039, the decimal points. Okay, so here's the volume that has been displaced, right? But from this volume, what we do not know is its height. Would be equals to the length times the width times the height. Because remember, the volume of the water that is displaced takes the shape of the object that is displacing. So the object that is displacing, in this case, we're told that it is rectangular in shape, right? And so, but what we do not know is the height, the length, the width, and the height. Okay, obviously that's 2D, you can't show the height. Now the volume displaced 598,039 should be equals to the length we know is 300. And the width we are given there, it's 8 meters wide. But the edge, we don't know how much water has been displaced, right? We don't know how much water has been displaced. If it was submerged, then we were going to multiply by 40 meters, right? But it's not completely submerged. It's partially submerged, right? So we need to find the value for H. So H will be 598,039 over the product of 300 times 18. .9, so we can approximately say that's 25 meters, all right? So which means that the distance of the ship that is below sea level would be 25 meters, right? Which means only 25 meters of the 40 meters is in water. So if you multiply 25 meters by 300 by 80, it will give you this volume that has been displaced. And the volume that is from that volume that has been displaced, we're able to find what the height is because we have got the width and the breadth. I hope this adds to your learning. Let's look at question 7. Right, so question 7, just like the second question, I'm going to skip this one. You can read around on this one and try it out and see if it makes sense. If it doesn't, then you can let me know. We can discuss it some other time. but you can read on this. Let's look at question 8, which will be the last question for today. Find the average density of a red giant star with a mass of that and a radius of that. Okay. So we are looking for the density here, given the mass and you're given the radius and the density of a star. Okay. All right, I see. So if it has got a radius, then it's spherical in nature. Then if you have radius, you can find the volume. I won't break this one out, but I'll just scribble out the equations that you can use to get the answers there. Density is equals to the mass over the volume. Because you're given radius, then obviously it's spherical. You're given a radius r. The mass you're given, you need the density, you've got the volume. So volume of a sphere will be 4 over 3 pi radius cubed. So which means to get the density will be 4 over 3 pi r cubed. So that's how you would obtain your average density of the red giant star. Okay, so this is what I had. That is an introductory tutorial to fluid mechanics questions, and I hope that this did add to your learning. Join in for the rest of the tutorials in the next coming sessions. I think there'll be one session tomorrow and the other one on Friday. So I wish you the best in your learning, and this is it from me and everyone else in the studio. Cheers. Let us know if you have got challenges and you've got problems that you'd want to be helped with. You can email any one of the tutors to assist you. Okay, for now, it's a goodbye from me.